Lesson 0.2 has us starting off our 2-day lesson on solving inequalities. An inequality is simply a relation between two expressions that are not equal. Similar to solving equations, you'll want to isolate your variable using your properties of PEMDAS backwards. However, with inequalities, there are a couple of other rules to keep in mind. We'll talk about those as they come up in the following 4 examples. Example 1, solve and graph the solution on a number line. In our first example, x minus 5 is greater than or equal to negative 7. Isolating your variable would happen simply by adding 5 to each side. On the left, we have x. Our symbol reads is greater than or equal to. On the right, negative 7 plus 5 is negative 2. That would be our solution set. On a number line, we would divide it up in incremental order, however many dashes you want to put on there. I'm going to divide up my number line to show that spatial representation, like so. That's a negative 4. If the boundary is at negative 2, the greater than or equal to symbol means it's going to be a closed dot at that number on the number line. Well, that's a really big dot. Sorry about that. There we go. Well, we get it at least. If your variable is on the left-hand side, the direction of your arrow in your answer will always match the direction on the number line. We want values for x that are greater than or equal. Therefore, the values on the number line will go to the right. And that's your number line solution. In the next example, we have a little bit more work to do to isolate our variable. We're not going to want to isolate that parenthesis like we did before, as we see there are 2 x's on the left-hand side. Instead, what I'll do is distribute the negative 4 in to eliminate the parentheses. Negative 4 times 3x is negative 12x. Negative 4 times negative 1 would be plus 4. And then we still have that plus 6x on the left, and that's all greater than or equal to 16. From here, if I combine like terms, we have 2 terms that have x with them. Negative 12 plus 6 would be negative 6x plus 4 is greater than or equal to 16. And now we would move that 4, it's being added, so we'll subtract. And I'm going to need a little bit more room, so let's see if I can make that happen here. Just kind of zoom over here to the left. All right, let's continue on. We have negative 6x on the left is greater than or equal to. On the right, 16 minus 4 would be 12. To get x by itself, we divide by negative 6. So far, everything should seem pretty straightforward. However, what happens here is we divided by a negative. While our variable stays on the left, our solution for our inequality will switch because we divided by a negative. On the right, 12 divided by negative 6 is negative 2. So just something to consider: when you multiply or divide by a negative value, your inequality will switch direction. Now that our solution is in place, we'll draw our solution or our answer on a number line. So I'll put my 0 here, negative 2, negative 4, to show that spatial representation. And again, for our solution, our boundary is negative 2. I'll put my closed dot there. And this time with my variable on the left, the inequality is less than or equal, so my arrow goes in the same direction as the inequality. All right, now time for you to try. Pause the video and try the next example. 3.5x plus 19 is greater than 1.5x minus 7. And see what you get for your answer. Once you think you have it, press play again and see if we have a match. Did you get x is greater than negative 13? If yes, then your work may not be in the exact same order that my work is, but your end result should be the same. X is greater than negative 13. On your number line now, make sure you have a spot that locates negative 13, and then it's divided up evenly. Oh boy, hang on. So I'll have negative 13, and then I'll just go up by 2, negative 11, negative 9. That'll work. That's a 9. Now in this instance, notice it's just greater than negative 13. That's going to indicate an open circle. So now I'm not going to fill it in. My arrow goes to the right, and again it will go to the right on my number line. For that last example, negative 7/2 x is greater than or equal to negative 3/4. If you're multiplying something by a fraction, to get rid of it, you would multiply by the reciprocal. I'm going to multiply then both sides by negative 2/7. I'll do the same thing on the right. The 7's cancel, the 2's cancel, and the negatives cancel. That leaves us with x, but again, we're multiplying by a negative. That's going to flip the direction for our inequality. And now we just need to simplify. I know that 2 goes into 4 twice, and 2 negatives make a positive. But on the top, I have 3 times 1 left over, which is just 3, and on the bottom, 2 times 7 is 14. X is less than or equal to 3/14. On the number line, 3/14 would be somewhere between 0 and 1. So you're welcome to kind of spread out your number line a little bit so it's easier to navigate to that location. I'll put 0 here, 1, 2, and 3. Recognizing that if x is greater than or equal to 3/14, that's going to be closer to 0 than it is 1. And I'm going to put a closed dot approximating that location. Again, your variable's on the left, therefore your arrow on the number line will point to the left as well, matching the arrow on the inequality. There are 2 other types of solutions that we didn't come across in our examples up above. One being infinitely many solutions and one being no solution. You'll have infinitely many solutions to your inequality when the variable cancels out and the inequality ends up staying a true statement. Your inequality will be no solution when the variable cancels out, but the inequality is a false statement. Let's try the 2 examples on the right. It says solve and graph the solution on a number line. In that first example, notice we have variables on each side. The first thing I'm going to do is distribute the 3 to both of the parts on the parenthesis on the left. Negative 3 times 2x would be negative 6x. And negative 3 times negative 5 would be positive 15. Is greater than negative 6x plus 9. Notice if I try to combine the x's, when I move the 6x over, it cancels out on both sides. What we're left with is 15 greater than, and then on the right we have 9. Think to yourself, is 15 greater than 9? Yes, it is. That means this is a true inequality. Because of that, the solution to the inequality itself is infinitely many solutions. And the unique thing about its solution on the number line is it's the entire thing. So you kind of put some divisions in there, 0, 2, and negative 2, but the solution itself is just a line that extends in both directions. Now I'm guessing you can probably figure out what the other example is, but we'll walk through what it looks like. Again, we have a variable on each side. I'm going to distribute the 2 in on the right to eliminate that parenthesis. On the left, we still have 4x minus 5. On the right, 2 times 2x is also 4x. 2 times negative 3 is negative 6. If we combine the x's, they cancel out on each side. Now here's the unique thing with these inequalities. We have negative 5 on the left is less than negative 6. Think about your number line. Is negative 5 smaller than negative 6? It actually isn't. It's closer to 0 on the number line, which means it's technically bigger. Therefore, this is a false statement. When you have an answer that's false, that means there's no solution to the system. So if you were to create a number line, there's nothing on it. It's kind of strange. And those are your notes for section 0.2.